Okay, so now we'll take a look at equations that contain radicals. And this is the main theorem that we're going to be using. It says if the nth root of u is equal to c, where u is a function of x and c is a constant, then the solutions to the equation are among the solutions of this other equation, u is equal to c to the n. So if you take a look, the equation here has a radical and the equation here does not. So we're getting rid of the radical, and how we do it, you get rid of the radical and you just get the radicand u on the left side, but on the right hand side you have to raise whatever's on the other side to the power of n. So whatever's on the other side needs to be raised to the power of the index of the radical. So let's try one. So this says the square root of 5x minus 4 is equal to 6. The index of that radical is 2. Whenever there's no index written, you assume it's 2. So that means we can get rid of the radical and just have 5x minus 4 if we square the other side, raise it to the second power, which tells me that 5x minus 4 is equal to 36. And then this is a two-step equation to solve. You add 4 to both sides, you get 5x is equal to 40, and then you divide both sides by 5 to get that x equals 8. So that's the solution to this equation right here. And we just know that the solutions to the original equation are among the solutions to that new equation. So we do have to check. So we do a check, quick check, to see if 8 is the solution to the original. 5 times 8 minus 4 should equal 6. So that says that the square root of 40 minus 4 is equal to 6, or the square root of 36 is equal to 6, and that checks out. So it works, and that means I do actually have the solution here. X equals 8 is the solution to that equation, and we've solved it. Let's try another one. So even if the thing that's on the other side of the equation is not a constant but has a variable in it, as long as we isolate one of the radicals in the equation, we can actually get rid of that radical using that rule. The rule says that if I want to get rid of the radical and just write 19x plus 30, then I have to raise the other side of the equation to the power of the index of the radical, which once again is 2 since there's no index written. So I'll get this equation, which is 19x plus 30 is equal to 4x squared. I see the x squared and I immediately realize that this is a quadratic equation, and to solve the quadratic equation I want to put it in standard form, which has an ax squared plus bx plus c equaling 0. So I want it to be in that standard form. So what I'm going to do is I'm going to subtract the 19x from both sides and also subtract the 30 from both sides. So subtract 19x and subtract 30. On the left hand side I get the 0 that I need for the standard form, and on the right hand side it's just 4x squared minus 19x minus 30 because none of those terms were like terms. Now we can try to factor this. Let's see if it's factorable. Well, if I do, the GCF is 1, so if I'm going to get two factors, they're going to be binomials. And let me see. X and 4x could give me the 4x squared, or it could be 2x and 2x, but we're not going to try that just yet. And then for the 30, it could be 1 and 30. One of them would have to be negative, obviously. It could be 2 and 15. It could be 3 and 10. But I'm going to try 6 and 5. So 6 and 5 are the ones I'm going to try. Let's try negative 6 and positive 5. And I think that works out. First times first would give me 4x squared. Outside outside would give me positive 5x. Inside inside would give me negative 24x. And 5x minus 24x is negative 19x. And then negative 6 times positive 5 is negative 30. So that is it. That's the factorization, and I'm going to just set each factor equal to 0 then. X minus 6 equals 0, or 4x plus 5 could equal 0, and that would be true. So this one, I just add 6 to both sides. That's simple. And I get x equals 6. And here's another two-step problem. I subtract 5 from both sides. I get 4x equals negative 5. Then I divide both sides by 4. And I get x is equal to negative 5 over 4. And then we would check our answers. So 6, let's check 6. So I get the square root of 19 times 6 plus 30 is equal to 2 times 6. Well, let's see. We have 19 times 6, which is 114, plus 30 is equal to 2 times 6, which is 12. So I get the square root of 144 is equal to 12. So at least 6 works. Then we'd have to try and check to see if negative 5 over 4 works. So we'd have the square root of 19 times negative 5 over 4 plus 30 is equal to 2 times negative 5 over 4. Alright, let's check that out to see if that works. Well, turns out that 19 times negative 5 is negative 95. So this is negative 95 over 4 plus 30 equals, and that's going to be negative 10 over, or actually just negative 5 over 2 if you simplify it, right? When you multiply that on the right side. And then let's see, we're going to take that negative 95, and 30 over 1 is actually 120 over 4. So this is the square root of negative 95 over 4 plus 120 over 4. And we're saying that's equal to negative 5 over 2. Alright, let's see. So 120 minus 95 is 25. 25. So I get that this is the square root of 25 over 4. And we're saying that's equal to negative 5 over 2. Well, hold on. 5 over 2 is not equal to negative 5 over 2. So even though I got both of these answers, this one doesn't work. The only one that works is 6, so 6 is the only solution. 6 is the one I need. So not all the solutions of this equation are actually solutions of the original equation. Not all of them are. You do have to check. And we just found one that wasn't. Negative 5 over 4 is not actually a solution. Here's a third example. So in this case, we still want to isolate the radical. We subtract 2 from both sides. We get that the cube root of x minus 5 is equal to 3. And then we raise both sides to the third power to get rid of the radical on the left side and just have x minus 5. But on the right side, I'll have 3 to the third power. So I get x minus 5 is equal to 27. And then to solve this, I just add 5 to both sides to get that x is equal to 32. Now, when it's an odd index, you don't necessarily have to check. So I know that this is the solution. This is the final answer. All right. So odd indices, you don't have to check. And here's the last example. So for this example, once again, I need to get rid of the radical. To get rid of that radical and just have 16 plus x, I have to take the right-hand side, x minus 4, and I have to raise it to the power of the index, which is 2. All right, so the right-hand side, I actually FOIL to get x squared minus 8x plus 16. Then I go through and I need to put it in standard form because it's a quadratic equation. So I subtract the 16 and subtract the x. Subtract the 16 and subtract the x. On the left hand side, it leaves a 0. On the right hand side, I'll get x squared minus 9x, and those just cancel out. And then it's just a matter of finding the solutions to that equation. Well, I can factor out an x because x is the GCF, and I'm left with x minus 9, which gives me two solutions. X is equal to 0 and x is equal to 9. But remember, we do have to check both of these, because just because they're solutions to this new equation that we got don't mean they're solution that doesn't mean they're solution to the original. So let's try and see if they both work. So let's see. First, we're going to check, and the first one we're going to check is 0. So let's see. The square root of 16 plus 0 is equal to 0 minus 4. Says that the square root of 16 is equal to negative 4, but the principal square root of 16 is positive 4, not negative 4. So it turns out that 0 does not work and needs to be thrown out as an answer. And let me see 9. Let's see if 9 works. So 16 plus 9, the square root of 16 plus 9 is equal to 9 minus 4. Well, the square root of 16 plus 9 is the square root of 25. And 9 minus 4 is 5. So 5 is equal to 5. So that one actually works. And we do have one solution, x equals 9.